Now let's see how to take the derivative of an exponential function. Let's start with a general base a. So if we want to take the derivative of a to the x, this would be the limit as h goes to 0 of a to the x plus h minus a to the x divided by h. We can use the property of the exponential function and write that as the limit as h goes to 0 of a to the x times a to the h minus a to the x divided by h. We see we have a common factor of a to the x here, so we can factor it out. It doesn't depend on h, so we can pull it in front of the limit. So this becomes a to the x times the limit as h goes to 0. So we have an a to the h minus 1 divided by h. So our derivative of a to the x is equal to a to the x times this limit. We should ask what that limit is. Turns out to be rather simple. If we take the derivative of a to the x and set x equal to 0, so what is the derivative of this function at x equals 0? That would be the slope of the tangent line to y equals a to the x at x equals 0. Then if we substitute x equals 0 here, it would be a to the h minus a to the 0, which is 1. So a to the h minus 1 over h. So that, in fact, is equal to this limit as h goes to 0 of a to the h minus 1 divided by h. Okay, so this can have any value depending on what the value of a is, but it'd be really nice if this limit was equal to 1, because then the derivative of the exponential function would just be the exponential function. It turns out that there's a special number where this limit is equal to 1, and that special number is E, right? Euler's number, the one that we introduced before. So let's see how we can show that. If we have our definition of E, remember, was the limit as n goes to infinity of 1 plus 1 over n raised to the nth power, right? That came out to be something like 2.8 with it's a transcendental number, so never-ending digits, not repeating. But here we have h goes to 0 in this limit. So it's a little bit easier. Instead of working with n, we'll work with 1 divided by n. And we can call that 1 divided by n, we can call that m. So then if n goes to infinity, 1 over n goes to 0. And then this would be 1 plus m raised to the 1 over m power. Okay. So we can use this definition of E and substitute it into the expression for the derivative of E. So we can look at the derivative of e to the x at x equals 0. That would be then the limit as h goes to 0 of e to the h minus 1 divided by h. And then instead of e, we can use this limiting formula. So that would be a double limit now. The limit as h goes to 0 and m goes to 0 of 1 plus m to the 1 over m raised to the h power. So the exponent then multiplies. So that would be 1 plus m raised to the h divided by m power minus 1. divided by h. Okay, so now we need to evaluate this limit. It's a little bit tricky. H and m go to 0, but we don't know what this ratio is. But if we make a simplification that this ratio is a positive integer, then we can expand 1 plus m to the h over m in the binomial expansion. This result is more general than that, but this will give us an idea what the answer is. So if we do a binomial expansion here, the first term would be 1, right, multiplying itself h over m times. The next term would be linear in m, so that would be m, so it would be h over m, this is an integer, times m. H over m times m is just h. And then the next terms will have higher powers of m. So the next term will be proportional to m and h. So we can put dot, dot, dot there because they're going to go to zero. The dot, dot, dot divided by h will go to 0 when h and m both go to 0. So this one, minus 1 divided by h. And then we have 1 minus 1. We have h divided by h. And the dot, dot, dot terms divided by h will all go to 0. So finally, we see that this is indeed equal to 1. So the exponential function with base e has this special property that the slope of e to the x at x equals 0, the slope of the tangent line is exactly equal to 1. So that means that the derivative of the exponential function is the exponential function. So we get this beautiful result that the derivative of e to the x is exactly e to the x. That's why we like to use e in calculus. So we actually call this function the exponential function. So e to the x, we sometimes will write it as exp of x. So let me summarize. We're trying to find the derivative of the exponential function. I'm starting with a general base a, and I've shown that the derivative of a to the x is equal to a to the x times the value of the derivative of a to the x at x equals 0. And there's a special number where the value of the derivative of a to the x at x equals 0 is exactly equal to 1. That number is a equals e, Euler's number. And then we have the beautiful expression that the derivative of e to the x is equal to e to the x. That's why the exponential function exp of x equals e to the x has a central significance in calculus. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.